Good afternoon. Today's presentation will focus on mitigating icing impacts on wind turbines. This capstone is under the supervision of Dr. Kevin Pope and will be designed by No Ice Solutions. No Ice Solutions consist of 4 mechanical engineering students who are all specializing in the materials stream. The team includes myself, Krista Garland, as team lead and director of anti-icing and de-icing systems, Mark Cranch, director of wind turbine engineering, Mitchell Lundergan, director of icing impacts and mitigation techniques, and last but not least, Philip Young, director of prototype design and testing. The agenda for today is to review the project definition, explain the concept selection process, define the final design, discuss the virtual prototype, explain the testing apparatus and procedures, and discuss the tasks to be completed. At the end of the presentation, we'll answer any questions you may have. The purpose of this capstone is to design and fabricate a system that successfully prevents and delays icing impacts and formations. The system must be compatible with already existing wind turbine designs and icing sensors. We must perform software analysis to test various coating properties such as ice adhesion strength, and perform physical testing of material properties and its performance. The design will be completed by April 2021 with a project budget of $500. The design will be modeled after a 2.5 megawatt wind turbine located in rural communities which experience severe cold climate changes or are located at higher altitudes. The concept selection process consists of 6 categories. These categories include ice mitigation capabilities, 30%, cost, 20%, maintenance interval, 15%, design obstacles, 15%, design history, 10%, and environmental impacts, 10%. 4 anti-icing and de-icing methods are then evaluated throughout these categories. These methods include superhydrophobic layers, internal heating elements, chemical sprays, and ultra-guided waves. Once each method was evaluated, a final design was then chosen.
The final design chosen is primarily the use of an isophobic coating with a supplementary heating element attached where necessary. For the physical prototyping, we will use a Whirlin Super F1 coating as our primary testing coating, and a silicone rubber heating blanket for the heating element.
For virtual prototyping, we chose to use FenSap Ice by ANSYS. This software is used to simulate ice accretion on solid bodies in a fluid airflow. Its capabilities include simulating environmental icing conditions, testing anti-icing systems, and the effects that icing causes on aerodynamic properties. On the right-hand side, you can see a mesh that we built using the ANSYS software. Below that, you can see the results obtained from FenSap Ice. The lighter blue areas are the areas where more ice has formed. For the icing conditions that we chose to study in FenSap Ice, we have the time it takes for significant ice to form, droplet sizing, liquid water content in the air, relative wind speeds, and ambient air temperature. The figure on the right shows maximum ice thickness for different time durations. This gives us a good estimate of where we should conclude our physical test. For concept testing in FenSap Ice, we can test different geometries, surface roughnesses, and different levels of heat flux at the surface. In our simulations, when applying a 40 watt per meter squared heat flux, we've seen a decrease of maximum ice thickness by 42.5%. In the images below, we can see a comparison between a non-heated leading edge and a leading edge with a heat flux of 500 watts per meter squared applied. The red area indicates places where more than 3 centimeters of ice has accumulated, versus the dark blue areas represent areas where no ice has accumulated.
To create a prototype of the airfoil's leading edge, we plan to use a foam base to mold an epoxy into the shape. We will use an oval foam with a large radius of 20 centimeters and a shorter radius of 5.5 centimeters. The idea is to mold carbon fiber cloths into the epoxy to further resemble the material properties of a wind turbine blade. Only a section of the wind turbine blade will be molded for prototyping. This is a result of ice accretion happening primarily on the leading edge, thus the trailing edge will not be required for this test. The drawing thickness is exaggerated to contrast the thin heating blanket. To ensure the prototyping and testing phases will run smoothly, a bill of materials has been created to monitor the budget of the project. This also helps to quickly find the shipping prices and wait times for each product before starting the second half of the project. At the first revision, the cost of our components came to $444 plus $77 for every yard of cloth required.
The ideal icing conditions we have chosen come from a combination of real-world data, experimental testing, and our own software analysis. These parameters should ensure that we are testing our apparatus in the absolute worst possible icing conditions that a wind turbine could ever be subject to. Luckily for us, these optimal icing conditions have quite a wide range without seeing much difference in ice accretion. None of these parameters need to be exact to achieve a high amount of ice buildup. However, the parameters will still be measured and kept within a tight range during all experimentation. With icing conditions such as these, we expect to see significant ice buildup on the uncoated surface within 5 to 10 minutes. With the coating applied, ice accretion is still expected within 15 minutes. This allows for quick tests which can and will be repeated to ensure that our theoretical icing conditions in fact lead to the greatest ice accretion. Once the ideal conditions are verified, we will conduct many tests on our model blade. All the tests will be similar in that they will have the prototype placed in icing conditions for 20 minutes with the weight being measured every 4 minutes. This will give us data on when the ice begins to form and how quickly the ice will build up. From start to finish, these tests will take less than half an hour. This short testing time allows us to run many tests in the run of a day, which will let us repeat tests multiple times to ensure our data is accurate and not influenced by external factors. In order to get useful results, we will test the prototype without a coating or heating as a control to see the ice accretion on the blade's epoxy. Once that data is required, we will test the prototype with the heating and coating separately and together. The end goal is to observe how the coating will impact the amount of heat needed to keep the blade ice-free and how that compares to a naked blade surface. This may take many tests with a varying amount of heat flux through the prototype. In addition to all of these, we would like to complete multiple abrasion tests which will test ice accretion after the coating has been scratched by a specific amount. This will give us information on the durability of the coating. Of course, all of these parameters are based on research we have completed and simulations we have developed. If we find the parameters will need to be tweaked, then we will adjust the testing as necessary. Ultimately, these tests will show us the effectiveness of our selected coating by comparing results of different tests. The information will show us the amount of heat flux that will need to be added in order to keep the prototype completely free of ice. Using those results, we will be able to scale up our findings to a full-size wind turbine for an effective ice mitigating solution.
Our upcoming tasks include acquiring materials, building a test apparatus, and performing physical testing. Here's an overview of some of the resources we're using to complete this capstone. Thank you for watching our presentation. At this time, we'll take a couple minutes to answer any questions.